Welcome all to this 18th lecture of Principles of Statistics. Today we're going to finish classification problems and we'll start further topics. So I think it's a good time to start these more advanced topics because we will be at the end of this lecture 3/4 of the course in. So with the classification problem, what we're going to do today, and we'll still be focusing on binary classification, is to apply the results from decision theory that we've seen in the last few lectures, so that we see them in practice, at least in this problem as well. Yeah. Okay, so as I just said, let's put into practice these results. So let's put into practice the results from decision theory, which I'm shortening as DEC theory. From previous lectures, right? Okay. So we say that for a prior, let me remind you from the last lecture. So for a prior, pi q, and we're going to have this q is going to be a number between 0 and 1, so it's a probability. Then the base classifier, so this is in some sense a definition if you like, classifier, is given by this delta pi, which can be written as in terms of the Q, or maybe in terms of the region that we saw last time. And so just for to remind you, this is just the this is just one if X is in the region, and 2 if X is in the complement of the region. And what region is this? So this is where, again, this calligraphic R is given by this region that we had. Okay, it's just a set of X's such that Q F1 of X, maybe let me write Q on the right, divided by F2 at X1 minus Q is greater than or equal to 1. Okay, so I may have, by the way, so just from memory, I haven't checked, but I may have somehow, so I think I said that this is a base rule, as in it will minimize the base risk. So the question is how I said it, whether I stated it or I actually said it, it was implied from something I did. So if it was the second, then I'm sorry for that, because what we're going to do now is just actually prove it. So if I stated it, then it was good and it was correct. Okay. Okay. So proposition then. So proposition 4. So this delta pi is a base rule. Okay. In other words, it minimizes the base classification risk. Okay, so let me write this class as classification. Okay, and so second part of this proposition is that if we have, well, let me actually write this if here so that we have a display. So if the probability under Fi, actually let me write Fl of F. Sorry. Let me just say what I want to say. F2x. So if this ratio being equal to this other ratio, has probability under FL 0, and this is for both L1 and 2. Okay. Then the classification rule, or the Bayes rule, the Bayes classifier or classification rule in this case, is is precisely unique Bayes. So is the unique Bayes rule, of course, for the prior. The loss function, this kind of things, the classification risk. Yeah? So that's implicitly having a loss function for classification, which is just an indicator, right? So we've sort of seen this implicitly. Okay. So how do we prove this? Well, the proof is actually quite simple. So let's write the Bayes risk or the classification risk or error in this problem. And let's do this for any region. So for any region, and let's call this one maybe calligraphic S, and this, of course, is in this calligraphic X. The classification risk or error is is what we've seen already. So we have this Q, this Q and the integral over the complement of the calligraphic S over F1 plus 1 minus Q, and then integral over this guy of F2, right? So this is misclassifying, yeah, I remind you. So, okay. And let me maybe say before continuing that I'm interpreting these integrals. They should mean PMF and PDF, yeah, both of them. So this is why I'm not really being very specific with the DX and all that. So after all, we can go back to the origin of the notation for the integral, being a sum, and you should consider this as a sum or as a limit of sums, yeah? as an integral. Okay, so if we have this, then we can write the second term or the second integral in terms of the complement of this calligraphic S and get the following. So we get that we have QF1 minus 1 minus QF2. Okay, and then the second term we get is just 1 minus Q integral, and this will be just over the whole of X, right, of F2. Right? So let's okay. So we wish to minimize this, yeah. So if we wish to minimize this, well, and this is with respect to the calligraphic S. Well, this guy is independent, yeah, from the calligraphic S. So independent of this guy, yeah. And so that means that we won't be able to as in we can ignore that term, yeah. So how do we minimize this other term in here? So we wish that, let me just write here. So wish this calligraphic S complement to to basically contain, so let me just say it in words, and then it should be clear as I'm writing it. So to contain the set of x's such that the, that quantity in there, so the q f1 at x minus 1 minus q f2 at x is negative, right? Because we want it to be as small as possible, right? So we want to subtract, we want to take away as much from the second term that is independent of the calligraphic S. Yeah. So we wish to contain it, right? To contain this, you could think, well, do you want to have it all? Yes, you should have it all, because the more you add, the less the quantity, the base risk will be. And so then the other thing that you don't want, well, that you want, is basically to not have any of a positive bit. So we wish this guy to contain this, and I guess let me just say be disjoint from. Let me just write. Shorten this. It's the positive, and and we also, we're happy. We're happy for this guy to contain the same thing when it equates zero, or also contain parts of this set in which we have the equality to zero, yeah, or or a subset of it. Or a subset of it. Okay, so therefore what we're saying here is that, S should be essentially, or it could be, X in this calligraphic X of, these guys being greater than or equal to 0. Yeah. So I'm including the 0 in this case because, as I said, the calligraphic S complement, can contain this set of equality to 0 or any subset of it, including the empty set. Yeah. So we're happy with this, or maybe up to choices containing this. Yeah. Okay. So this shows the first part, right? And then for the second part, if this set that we're looking at is null, so it has it has probability 0 under F1 and F2, then what will happen is that we could be changing this calligraphic S up to these changes in the choice of what subset to take of this equality to 0, but this will not change the classifier, at least under these the measures that these give rise to. Yeah? So it means that the delta pi is unique. Under these. Yeah? So if you had mass that is larger than 0, then you could be changing some of the elements in it, and then the classifier would actually be different. Yeah? Okay, so this shows the two parts, and let's make a remark. So the first part is simply saying, well, by proposition 3 on the first entry of it, we have that this is a unique, well, let's say if, and let's call this star. So if star holds, then we have a unique base classifier or rule, and so delta pi is admissible. So that's really good news. And then what about minimaxity? Well, we have that by corollary 1. We can apply the recipe of corollary 1, in which we said that if we have we have a constant risk, then for a unique base rule. Sorry, a unique base rule will be a unique minimax rule. Yeah. Okay, so by corollary 1, this delta Q will be minimax for Q star, maybe, okay, for Q, such that you get what I was saying. So these guys are, equal. So let me just say that. So i.e. constant risk in Q. Okay, and then of course it is unique. Unique minimax if this star holds, right? Okay. Okay, so let's get an example, which we're not really going to do in detail because it is part of the next example sheet. So okay, so consider classifying a random variable or an observation. Capital X into population F1, that is distributed according to normal distribution with some mu1 and some capital sigma. This is multivariate, or F2 or F2 according to just the same thing but with a different mean. Okay, where, as I'm just saying, well, mu1, mu2 belong to RP. They should be distinct, right? Otherwise, there is no problem to solve. And this capital sigma belongs to RP times P and is, of course, a covariance matrix. Yeah? Okay, so then I claim, and you will have to prove this, that this delta Q is minimax for, and actually it's unique minimax, yeah? For Q equal 1/2. Okay. Okay, so that would sort of close this, but let me just mention that this has a name, this sort of problem, and for that, let me just introduce a couple of things. So, so let's then go back to the setting in which we have. So this is part of the sort of remark in some sense. So for Q between 0 and 1, and let me define D to be this X transpose, and the capital sigma minus 1, mu 1 minus mu 2, okay? Then for these, delta, let's say maybe now it's Q, but it's also, we can make the dependence on the region explicit, because now the region is given by this. This is these minus 1/2 of mu1, mu2, transpose sigma minus 1. Okay, it's not going to fit. Let's just go back to 4. This region. Transpose, and then sigma minus 1, mu1 minus mu2. And this has to be greater than or equal to log of 1 minus q divided by q. Okay, and so this is just a fact. They will also prove in the example sheet. And let me point out that D is called the discriminant function. Okay, and then since it is linear, and this, means in X. Okay, so that's usual, I guess, vocabulary for this. If you say that an estimator or the rule is linear or nonlinear, then of course, then it generally means just in terms of the X. Yeah. Okay, so since it is linear, this is all called, so this analysis and this classifier and this classification approach is called the linear discriminant analysis. Okay, and if we have that F1, this is not in the example sheet, so this is just for your information. So if we have that the populations now do not have, or at least not necessarily have, the same covariance matrix, then then we're talking about quadratic discriminant analysis. Okay. Okay, so we are done then with this section, and so let me talk now about further topics. Okay, so we're going to start with some simple ideas, so not really advanced, but it's good to know these things. So this is basic multivariate analysis. Okay. And I will also split this into 3 different sections. So let X be a random variable or random vectors, so it doesn't matter how you interpret the V, random vector, yeah, in RP. Okay, so then what we have is that the covariance matrix, let me maybe write it so that it fits all here. So the covariance matrix of this capital X is going to be, so again, this is a matrix, and so this is covariance between xj and xk, okay? of or of these going from 1 to p, and each of these is given by the following. So these are just standard sort of definitions. So we have xj minus the expectation of xj and xk minus the expectation of xk. Yeah. Okay. What about its correlation? So the correlation matrix should be sort of familiar to everyone. So we can write it maybe as rho, and it's the same going from 1 to p, where this rho jk is given by the covariance between xj and xk, and we need to normalize by the variance of xj and the variance of xk. Yeah. Okay. So we get something that belongs to minus 1, 1. Yeah. Okay. Okay. So good. I mean, this is talking about a random vector, but we really are, we're doing statistics, so we need to look at a sample. So given a sample, x1 to xn, the jkth, yeah, maybe we can call it th. So the jkth sample correlation coefficient is given by this quantity. So this is this jk, and then 1 over n of the sum from I equal 1 to n x. I guess this is the ith observation, and then the jth component of it. And I also write, the average, sample average or sample mean, and we wish to get the jth coordinate of it. And sort of similar idea now with the kth, just the same idea with the kth. And that would be the estimate of the numerator, and the denominator can be also estimated as you expect, which is by writing, the empirical variance, sample variance. So, okay, so I have this, there's xn, j, and this is squared now, and xik minus xnk, and this is squared. Yeah. Right, where of course this is just 1 over n of the sum xij. Okay. So let me point out, you may have realized this already, that I'm trying to use the index I for the data points and j and k for the entries of a vector. Yeah, which is so I'm hoping I'm being consistent, but I may have forgotten at some point. Okay, so let's get a fact for this quantity. So the fact is, and you can check if you want to, sort of dig into the details. You can see, for instance, in one of the course references, theorem 4.2.1 in T.W. Anderson. Okay, so what do we have? So we have that if our guys xi are IID, so I'm talking about a sample. Okay, so this quantity here. So if these guys are IID according to a normal distribution with some mean mu and some covariance capital sigma, but it has to have some particularity. So assume that the rho jk is actually 0. Then the distribution. So this is of course, this condition doesn't really imply the sample. Yeah? It's just a condition for the theoretical, I guess, covariance in this case. Although, sorry, correlation, but they would coincide here. Okay, so with this, we know actually the distribution of a rho. Yeah, so the distribution of this guy, the rho hat, has PDF given by the following. So this is just f of r, 1 over square root of 2 pi. And then we get the gamma function, so 1/2 n minus 1, 1/2 n minus 2. Okay. And then the r dependence is here, just given by this. Yeah? R is less than or equal to 1. Yeah? So then once we know the distribution, then that's great news because we can use this for inference. Yeah? On the correlation matrix. So, and we will, in this multivariate analysis section, we will be talking about variance and covariance all the time. Yeah? Okay, so that's the first part. So that was 1.1. So let me now say 1.2. So what we're going to do is to restrict ourselves to, again, a Gaussian experiment. Yeah. Okay, so for x normally distributed according to, or with mean mu and covariance matrix capital sigma, and again, I mean, even though it's not really necessary because we're in the multivariate section already. So, but yeah, let's just emphasize that these guys are multivariate, and let's split our x as this, and this is, so this x1 is going to have length q, and this guy is going to have p minus q. Then why am I writing this? Well, because I want to say that the capital sigma can be written, I mean, this is not really any striking result, but I guess I'm just saying it for completeness. Have this, by the way, these two should be equal. And the covariance of x1 given x2 is, what we can denote as 1 given 2, and this is actually 1, 1 minus the 1, 2, then the 2, 2 to the minus 1, and then the 1, 2, I write it again because we have this equality between them, yeah, that I wrote here. Okay, so we get that, and then the other thing that we get is that the partial correlations, which are the following things. Okay, and this is really between now two quantities. So between xj and xk, and this has to be for j and k less than or equal to q, is given by this rho jq and conditioned on the x2 So we take our new covariance matrix for the conditional random variable, and we look at the JK entry. Yeah, so it's just exactly the same as before. Yeah. So we could have, yeah, okay, let's just take this. And this is for JJ, then times this. So this is the 1, 2, KK. Okay. Okay, so lastly, let me say that this can be estimated. Okay. By a sampling analog of what we've seen, yeah. As in, you could try to plug in things here, yeah? Analog. Of this guy. Okay. Okay. So we sort of done with these, and then let's just have a last little section in this multivariate analysis. And this, we're going to talk about what is called principal component analysis, which is actually a very, very popular technique. And so let's say, let's start by just saying that the covariances I guess covariances can be useful. And this, of course, covariance matrices, yeah? But they can be useful to reduce dimension or dimensionality. Yeah? And this is in a sensible way, because you could always reduce dimensionality by doing very stupid things. Okay, so let's go into details of what I mean by this. So this is what we're going to talk about, is principal component analysis. Okay. So what is the idea? Well, the idea is actually pretty simple. So the idea is to find, different directions in the space. These are, in the space that are going to have different variances. Okay. And what we're going to do is to have, maximum variances, and we want to have some sort of independence or uncorrelated or lack of correlation properties, yeah, for these different components that we'll have. Okay, let's find directions of maximum variance or variation, as you like. And then once we have these directions, we project our data. Yeah? So we project the observations on them. So let capital X be a random variable or a random vector, probably best in this case. It's fine with the random variable. Such that we have the same condition as what we had, just that it has expectation 0, and what we can say is the following. So then for capital sigma being the expectation of this X and X transpose, so just the usual definition of a covariance matrix, there exists V, as in a matrix that is orthogonal and so orthogonal or orthonormal in this case. So this just means that if we multiply it by itself, then you get the identity. So it is going to be such that sigma can be written as the product of this V and some capital lambda, and then V transposed, where this capital lambda, we need to specify it, and it is going to be just a diagonal matrix with this lambda, I guess lambda j's, where lambda 1 is greater than or equal to lambda 2, and so on up to the lambda n. So we sorry, not n but p. So we order them in decreasing order. Yeah. Okay. In other words, now that we see this decomposition, right? So that one there. What we are doing is that these lambda j's are going to be eigenvalues. And of this capital sigma, of course, and the VJs will be the respective eigenvectors. Okay, so what can we say? So we have that if we define, so let me define now a certain quantity that is actually going to be important, because this is what we will call the principal components of X. So this guy is the vector of coefficients. Let's just write it out maybe. Of this capital X in the eigenvectors. Okay. And the other thing that you can check, that's very simple to check, is that the expectation of U times U transpose will give you the capital lambda. Okay, so what does this mean? So what we have is that U is going to be of a very particular form, and it will be it will be such that it contains the same amount of information as the X, but it is of course sorted in a completely different way. Yeah? But the entries are going to be very different because they are going to be uncorrelated. Yeah? And more precisely, they carry the variability in decreasing order. Okay, so that should be sort of clear to everyone. So let me now give you a fact. So we're close to sort of finishing this. So fact is the following, and is that if our X is distributed according to normal distribution with mean 0 and that's just the assumption, and covariance matrix capital sigma, then what we will get is that the U that comes out of it is distributed according to a centered normal distribution with the covariance matrix given by this capital lambda. Okay, so in particular, the entries are independent, not only uncorrelated. And this is because we have joint normality for the U's. And the other thing that we can say is that actually you can write X as the product of some V times Y, okay, where Y is distributed according to the same thing as the U's. Yeah. So what do we get from this? Well, in particular, we can say the following. We're gonna be able to write X, and this is from the last bit here. So X, we can write it therefore as the sum from Jacob 1 to P of Vi, Vj, Yj. Okay, so that shouldn't be surprising. And this is just the same, through the Yj, through its covariance matrix. Then this is just the same as writing square root of lambda j, Vj, and then Zj, where the Zj's are IID standard normals. Yeah. Okay. Maybe let's put a comma. So what do we conclude from this representation of the x's? Well, we have that x is going to be the sum of the orthogonal effects, yeah, in some sense. Okay. And this is, of course, along the Vj's. And with amplitude, if you like, with amplitude lambda j. Yeah. And the other thing that we can say is that the UJs are called the principal components of this X. Okay, so that's great. We've sort of developed the whole understanding of this principal component analysis idea, and now we've just talked about a random vector. So really, what is interesting is when you have a sample. So let's just finish up then by writing what we can conclude about a sample, which is very much in line with what we just said. So if now we have a sample x1 to xn, something like some capital X, let's say that each of these guys centered again, and P should be less than n, then let me, with some abuse of notation, let me write capital X to be the matrix, that contains all of these guys. And so this guy, of course, is going to be in Rp times n. So just writing this for clarity. And let me say with some abuse of notation, because this is, capital X should be really just the, as in the random variable that the individual elements of a sample are a copy of. Yeah. Okay, so but avoiding that, so with some Okay. Select that, and let also this sigma now is going to be sigma hat, and it is going to be just the same as before. Okay. Then the same calculations give this here. They give just matrices like the ones we've had so far, and these two are going now to just as before. They're going to be in matrices of size p times p, and then now we're going to get a u hat, rather than being a vector, is now going to be a matrix in p times n. Okay, so it should be just like the x, the capital X. And, just as before, we get that u hat transpose should be equal to the hat capital lambda. Okay, and the uj, so the let's say maybe dot, just for clarity. Okay, so this guy, which is just simply the jth row. So we have p rows, okay, and the jth row is the direction with jth maximum variation, right? Within some space. And what space is this? Well, this is you can check that this is within the space, linear space, of course. Spanned by the rows of X. Or what is called the jth principal component. Okay. So what? Okay. So let me recap a bit, and then we'll just end with one more line. So what we've said basically is that we have this sample of x's that are centered, and this is just for convenience. And we have a sample covariance matrix that is given by this capital sigma hat. Of course, it's given by this product of matrices simply because the x's are centered. And what we do is this eigen decomposition, and we'll get this u hats that basically, if you, as in the rows of the u hat are essentially going to be uncorrelated, and they will have, certain variation that is decreasing in order. And what they really represent is that, we've transformed the space of the data into, the space is still the same, but we've now expressed it in such a way that the basis is very particular. So what we can do here is to say, well, if I want to reduce the dimensions, I don't want the p as the dimension. I want to have less information, but just because maybe I need to, for reasons of space or cost of some kind, then what can I do? Well, let me take then the first few principal components that explain most of the variance. So this is what we now say. So it is common to so it's common to keep only the first say J star principal components. Okay, where this J star is defined as follows. So where J star equals the minimum of the J's less than or equal to P, such that this ratio, so let me now have a sum over from 1 to J of the capital lambdas. This is the case, so divided by the sum of all of them. Okay. So this then is greater than 1 minus alpha, where alpha is typically 0.2 or 0.1 or 0.05. Okay, this is typically. Okay, so just to reiterate what I've said, the capital lambdas describe some variability, some notion of variability, and what we do is to keep, to look at how many, do we need to explain 80% or 90% or 95% of the variability, and then we just keep the components that correspond to that. So we will essentially be projecting the data onto this lower dimensional space. And, you may think, oh, but if we want to keep 95% of the variability, then maybe we need, if say P was 10, then maybe we need 8 or something. Yeah. And that's actually not true. So in practice, what one sees is that really, with 2, 3 principal components, you will have a lot of information. So the information will tend to accumulate around the first 3 sort of principal components. So that's really good news, because we may decrease from 10 to 3, 15 to 3, and all the type of instances, I guess. Okay, so I hope you enjoyed this lecture, and we're now entering the last quarter of the course, and so I hope to still see you there.